Now that we have properly understood what our process is, and we have even properly located point 2 on the Carrier diagram, the question is what is the heat flux needed in the first part of the process in order to heat up the air, and what is the evaporation rate taking place between 2 and 3. So that's not very complicated once we have understood everything. The heat flux between 1 and 2 directly corresponds to the difference of enthalpy of the moist air multiplied by its mass flow rate. The specific enthalpy is defined in kilojoule per kilogram of dry air. For this reason, we need to take into account the mass flow rate of dry air that is going through the system, through the heat exchanger. If we take the data that were given, this mass flow rate of dry air is called M1 because it directly corresponds to the mass flow rate entering the whole setup, and that stays constant because there's no exchange of dry air. And we know also that the specific enthalpy of point 2 and point 3 are exactly the same, so it's M1 times the difference of specific enthalpy between point 3 and point 1. Concerning now the flow rate of evaporation, the mass flow rate of evaporation corresponds to the difference between the mass flow rate of water we have with the air in point 3 minus the mass flow rate of water we have with the moist air in point 2. And the difference is the water that was added to the air due to evaporation. So the water flow rate we have in point 3 corresponds to X3, so the ratio of mass of water per the mass of dry air, multiplied by the mass flow rate of dry air. Similarly, in point 2, it's the mass flow rate of dry air times the moisture content of 2. If we write this with the data that were given, mass flow rate of dry air is still M1, the mass flow rate of dry air entering the system, and we know that between point 1 and point 2 the moisture content stays even, so we can write this as the mass flow rate M1 times X3 minus X1. So this means also that we could answer both questions concerning the heat flux and the mass flow rate of evaporation without even knowing what are the properties of point 2, because we can each time express these values as a function of the data of point 1 and point 3.